Hi, and welcome to this live demo of some example code we've written to show how to use Polygonica for build processing in additive manufacturing based on Polygonica's 2D operations. My name is Richard Baxter. I'm Head of Sales and Marketing at MachineWorks, which is the company that develops the Polygonica software libraries. As always, we're on LinkedIn. We have a showcase page for Polygonica. We have a showcase page for MachineWorks, and we have a company page for MachineWorks Limited. So please follow us. We're pushing out quite a lot of content that way. And if you have any questions, please don't hesitate to connect with me, and you can ask them that way, or you can get in touch via the contact page on the website. Okay, so firstly, a bit of background and overview about Polygonica's 2D operations. Polygonica has long been known, particularly in additive manufacturing, but also in other markets, for really fast, robust operations on 3D meshes. So automatic mesh healing, fast booleans, fast offsetting, remeshing, shrink wrap, decimation, etc., etc. And these are pretty widely used in the additive manufacturing industry. But Polygonica has always had 2D operations, as has MachineWorks, in fact. So, some of these 2D operations were put in back in 1994, 95. But following requests from customers in additive who have written build processes using Polygonica, then these operations have been extended. We've added more functionality, and they've also had to be optimized. For example, slicing was entirely rewritten. So slicing's been in there since 1994 in MachineWorks, but it was entirely rewritten a few years ago to support the demands of large area hard material printers, so metals and ceramics, where you might have very tight tolerances between the different layers in the vertical direction, and you've got very large, area print beds, so half a meter upwards kind of thing. So we're happy to say now that several major printer manufacturers, as well as using Polygonica for 3D, they also use Polygonica for 2D in their build processes, and that includes polymer printers and metal printers. So key thing to understand is there's no API inside Polygonica that says, give me a triangular infill strategy. Polygonica is providing the low-level operations, like, for example, do an offset, do a Boolean operation, etc. The business of deciding where to put the infill is up to you and your developers. So this ensures that you have control. You're not locked into Polygonica. If you want a different machining strategy or a different infill strategy, you can develop it yourselves. You don't have to come to us to ask for it. Which is great, and it also means that all those things remain your IP. So you know your printer better than we do, so you can develop those strategies based on what are fast and robust low-level operations, and also they're fully supported. So Polygonica is a commercial toolkit. If you find problems, we fix them and give you an update. And if you do have new requests, for example, the operation for finding the maximum thickness was a request from one of our customers. Then you ask us, and normally we'll add it for you. So what operations are there? Well, underpinning everything is fast polyline clipping. So pass in tens of thousands of polylines or hundreds of thousands of polylines, and then clip them to a profile boundary, basically. So that's a pretty fundamental requirement in hatch and infill. There's also 2D Boolean operations, so union, intersection, subtraction, 2D offsetting and dilation, so that's a Minkowski sum based offsetting. And also we've got advanced operations like 2D medial axis and 2D medial axis offsets. So just quickly describe the medial axis. You can think of as the skeleton of the profile or the slice. So it's a line such that any point on that line is equidistant from the boundary of the slice. And then medial axis offsets are a kind of hatch infill pattern that's generated by offsetting the medial axis outwards as opposed to offsetting the profile or slice boundary inwards. But it's a fairly complex topic, so I'm going to do a whole video and blog, just dedicated to medial axis after I've done this one. Also within Polygonica, so the idea of a profile is it's a bit like a solid mesh. It's a boundary of enclosing solid material. So in order to make sure that profile is in good shape, there's various healing operations, again analogous to 3D. So you can fix incorrect loop orientations, close open loops, remove self-intersections, remove insignificant loops, etc. So there's a bunch of useful operations to tidy up your profiles prior to doing the hatch infill operations on them. There's also arc fitting, so Polygonica's profiles can have arc segments as well as linear polylines, which is a way to save data. If you've got, if you've got a profile from somewhere else that has loads of little tiny faceted edges around a large arc, then you can just fit an arc to that and then set your own tolerances for refaceting. There's also intersection query, so I can clash detection. So take two profiles, do they intersect, or if they don't intersect, how far apart are they? And classification of points against profiles. So are they outside, are they inside, are they on the edge, etc. As I mentioned, also the really useful computation of the maximum thickness of the 2D profile. So that's really good for figuring out how many lines you're going to need at a certain separation to actually fill that region. And also convex hull, useful for certain optimizations, slightly better than just axis aligned bounding box. So other operations to create 2D profiles from 3D, mostly slicing, and also recreate 3D models from 2D profiles, reconstructing 3D solid meshes from a bunch of slices. So you can create planar slices from a 3D mesh, or you can actually do it from an entire 3D scene that has instancing. So Polygonica will slice instances for you, and you can also union all those slices together. So this is really useful in things like the 3MF beam lattice interface, where 3MF defines I've seen models with many tens of thousands of beam lattices in there. These are parametrically defined cylinders and spheres. And so you can load those in and slice them directly using the Polygonica slicing interface, without having to actually create a full instantiation of every single explicit 3D mesh. So that's really, really useful if you want to do that, because if you create a lot of those meshes, then it takes a long time. The slicer can be used fully in memory, or you can progressively serialize the results to disk. Obviously, it's internally threaded and it's optimized for large jobs. There's also the converse, or the converse operation, creating a 3D mesh from planar slices. So in this case, you've got a couple of options. You can extrude each slice and then use the solid multiple union operation to union the entire bunch of them together in one go, which is pretty heavily optimized and does a really good job. And in that case, the resulting edge will have the staircase effect due to the layers that you see in actual prints. Or there's a dedicated API, which you can pass in a bunch of slices and it will deliver out a smooth 3D mesh, so smooth vertically. So it uses some clever stuff internally to interpolate a smooth result between the vertical slices. So those are both available. And worth noting also the silhouette profile of a solid. So this is a profile or a boundary that you would get if you projected the solid onto a plane. So that top right image there is a sort of extreme case of that. And the same idea for a rotation of a profile about an axis, which gives you a kind of silhouette of rotation. So this is a pretty important concept in CNC turning, but I've not really come across another example of using it yet, but maybe we will one day. Okay. And finally, before I do the demo, just a note on the example code. So the code in the demo shows what you can do if you put all these operations together with a mind to do 2D hatch and infill for additive manufacturing. But it's available to customers and evaluees on an unsupported basis. It's not, as I've already said, it's not part of the Polygonica product. The supported part of the product is the offset operation, the Boolean operation, the medial axis operation, etc. The example code that puts it all together, you're very welcome to take. You can use it for testing Polygonica if you're evaluating, or if you're thinking of using Polygonica if you're already a customer and you're thinking of using it for doing build processor operations, you can use this to test. Or you could even take the code and use it as a kind of fledgling build processor and start developing from that code if that's how you want to do it. As you can see from the code sample I've pasted, it supports different types of hatching like lines, grid, triangles, hexagon, zigzag, concentric, medial axis, and I've also got medial axis offsets in there. So we'll move on to the demo and show you that in action. So the first thing to mention is this demonstration program is exactly that. It's a demonstration program. It's written using the Polygonica API, but we don't sell it. We don't provide it to people. The reason we don't provide it to people is that it's not properly QA'd and tested. It's just developed by the sales team, mainly me, in fact, with some help from some colleagues. So first of all, I'm going to load in test part D, which is this mesh here, and it's all the traffic lights are green, so it's a nice closed solid, etc. And we'll go to the toolpaths tab, adding more and more tabs these days, which is great. I just create 100 slices, obviously pretty quick. And then I'm going to create 100 hatch and infill with the defaults of a concentric wall fill and a hexagonal inner fill. And then we'll just look at the results of that. So let me hide. So that took 3 seconds to generate it and 1 second to reorganize the lines for the graphics. I might mention that later. Now then, let me just display one layer. So we see the bottom layer. So here we've got a two concentric patterns. That's because in 3D printing applications, it's nice to have a external boundary around the infill, and you need an external boundary in the walls, but also at the top and bottom. So this example code that we've written creates both, and it creates, in this case, I've given the top and bottom the color green, and the stuff around the sides the color blue. So, but they're both the same thickness. The green is that thickness vertically, and the wall is that thickness horizontally. So if I come through here, after a couple of layers, we actually lose we're above the base layer, and we're inside the part, so we're getting some hexagons here with the walls around it. And then we get to a more interesting layer here where we've got a mixture of green and red. So actually, let me just show the part, make it transparent. So you can see, I mean, if I look from this side on, I think you can see that there's a thickness here. So the green goes down a certain thickness into the part, and that's because it's by default in this example code, we've just made it the same thickness as this wall on the outside, but you can change that in the code if you want to. But you can see the red areas are where the actual struts join in, and they are internal, and so they're very definitely using the hexagonal pattern. So I can just click through that and go up through it, and you can see the different patterns, etc. Okay. So I'll load in another part, and first of all, there's lots of red and green on this part. The red is self-intersecting polygons, and the green is open edges. So this is not a watertight solid, and it has lots of self-intersections, and it's not manifold. In fact, it's a mess. I mean, you can see this screw pattern in here. There's almost nothing that's correctly joined up. But Polygonica is justifiably renowned for its automatic mesh healing. By now it's been tested against pretty much everything, and well, certainly in my experience, it always wins when those tests are done. But this is a complex thing to resolve, and it's done that in 12 seconds. So now we have a nice watertight mesh that's self-intersection free and manifold. So I'm just going to create 20 layers there, and we're in this case I'm just interested in the layer number 2 because it's quite an interesting layer to demo. So if I just hide that, and then we can see. So I've chosen this because it's got lots of kind of internal data, which is due to the vertical pockets. So there's internal loops and things. So first of all, I'm just going to cycle through the fill types, the different fill types on the internal. So we've got an implementation which is just straight lines. Although you can't see it, we've not added joining curves to these lines. If people request it, we can do that. The zigzag pattern, it might be hard to see here again. Yeah, there's no change, but the zigzag pattern, if I do zigzag in the outside, the zigzag pattern, we have actually done that. That pattern's available as well. Let me go back to concentric, go back to where I started. And again, for all of these grids, we've not put any joining moves in, but again, if somebody is serious about using this, then we'll add that sort of stuff in for them. So yeah, grid, let me zoom in a bit so you can see it. This green area is within the range of the top part of or the bottom part, I think. Triangles, let's see what else. Hexagons you've seen. Zigzag I've mentioned, but you can't see it because it's butting up against the outside wall. Again, there's controls. For example, this offset control here. If I make that bigger, then it's offset the infill from the exterior wall, and now you can actually see the zigzag pattern. So there's quite a lot of little controls like that in this example code. I've not exposed all of them. Just put that back to 0. What else? Concentric. So we can do concentric patterns. But one of the problems with concentric patterns is you end up with these missing regions. Now we can change the separation here. So if I change it to 1, it will be, that's probably what we're about. So let's change it to 0.1. Oh, sorry, I've changed the wrong one. Let's go back. That's bad of me. So let me change this one here. Let's change it to 1, and that's looser. Let's change it to 0.1. And you can see it's very tight, but you still have these kind of seams. So yeah, when you have a very tiny separation like that, you are going to kind of fill everything in. But I suspect that's too tight for a real application. So that's one of the issues with this offset type approach, is that it can sometimes leave gaps that need to be filled in. And that's why I'm just going to put this back to the default. That's why we added the medial axis approach, which is an alternative approach. Takes a bit longer to compute. So the medial axis, I'm going to do a more detailed blog on this video, but it's a line that joins the sort of, it's like a center line, a skeleton if you like. So any point on this line is equidistant from the profile. So you can see that's from there, and there. And one of the key features it has is it will join bridges. So you can use it to guarantee that material is going to be deposited even in very narrow regions. Now, you wouldn't necessarily normally include the medial axis in your toolpath, but we have done in this case, just for illustrative purposes. But you again, the choice is yours. You know, it's entirely up to you how you want to use this. And Polygonica has a function that creates the medial axis, and a separate function where you can pass the results of the medial axis to what a function called medial axis offsets, and it will create these offsets for you. And I'm also going to show you something I've called medial axis offset, which is a variation of medial axis. So this is combining the medial axis with an offset toolpath. So if you look in, for example, this region inside here, all we've done is offset outwards from the medial axis. So that's like a typical concentric result. But then the medial axis is available to go into corners and to make, and to cross bridges. So the idea here is you're mixing two different two different patterns. One is this, fairly standard offsetting pattern, and the other is the medial axis to make sure you don't miss material in extreme parts of the geometry. And I think I've shown most things here. Okay, let's just go back, say concentric, and let me change. Oh, no, that's not very good. Let's go to zigzag, and let me change the wall thickness here. So I'm going to make that, I don't know, 0.5. I'm guessing these numbers. That's a bit small. 1, still a bit small. Okay, let's go 10. Too big. 2. Okay, so you can change this. You can change these parameters. The -1s, these are just things I put in my code. The defaults are not in the example code that we provide at the moment, and they're really just based on the maximum thickness, which is something Polygonica computes for you. So it's a very useful way of setting a default based on the maximum thickness of the profile. Obviously, in a real job, you would probably use physical parameters. Yeah, how thick the wall needs to be for a piece of material, what the step over for the actual toolpaths needs to be. I mean, these are actually physically controlled parameters. But in this demo, oh dear, I think, yeah. So this demo, you can see I can set them to anything basically. And that's maybe not a great idea. There we go. Okay, so I think I've covered all the different parameters there. So finally, just one more part, just an intake, and again, I think I'll just do, let's see, just 20 slices. I'm going to make this transparent. I'm going to set the face alpha to about 20, so it's very transparent. And then I think I'll do zigzag and medial axis. I'm really just showing you this on another model, basically. So calculate that, and then let's display one layer, and we can. I mean, a nice display here. You can actually see the layers alongside the mesh, which is, sometimes useful if you're like, well, why has it put green there, for example? It can be quite helpful. And in fact, if I click through, you can see the medial axis patterns, quite funky. But if I click through, in this one, you're kind of like, well, why is there no infill there? But actually, I had to check this myself. There is, in fact, no material there. This part is pretty much hollowed out. So it is quite useful having the two displays side by side. So I'm going to click through, and then suddenly there is material again, and we've got a nice sort of classic medial axis skeleton there. Okay, so that's the end of this demo. If you have any questions, then please don't hesitate to get in touch. You can contact us via the website. There's a contact form up there, or you can find me on LinkedIn. My name's Richard Baxter, or you can find me under MachineWorks. And thanks for your time, and thanks for listening.